For the third part of this example, what we want to do is evaluate our vector A at point P in all three of the coordinate systems. So we're basically taking our answer from part 1 and we're going to be plugging it into the equations we had from part 2. So I'm going to be doing a bit of scrolling up and down so I don't have to rewrite all of our expressions that we found in the previous video. So let's go ahead and do this for our simplest case in Cartesian coordinates. Of course, we have our point P and our vector A given in Cartesian coordinates in our problem statement. Actually, before we do that, let's sort of remind ourselves what this looks like in our 3D space. So I have an X, Y, Z axes all plotted here. And so our point P is at -2. So let me switch to a different color. So we're at -2 in X, 6 in Y, and 3 in Z. So something like this. So we have a point that's maybe somewhere out here. So this is our point P. And so what we're saying is now we want to evaluate at that point what is the strength of our vector A. Okay, so let's do that for the case of our Cartesian vector and our Cartesian point. So essentially what we're going to do is we're just going to plug in those values. We're going to say we have an equation for A and we just want to plug in, well, now we're at X equals -2, Y equals 6, and Z equals 3. So we know that our vector A is equal to Y, which is 6 in our X direction, plus X plus Z, so -2 plus 3 in our Y direction. So of course we can evaluate that and we see that this is equal to 6 in our X direction plus 1 times our Y direction. So we just get something that looks like this. Now if we come back up here to our plot, we can kind of try to visualize what this looks like. So we could have a plane that is parallel to our XY plane, and we would say we have sort of 6 in our X direction and 1 in our Y direction, so we get something overall that looks like this. And again, this is parallel to our XY plane, just to sort of get a basic feel for what direction we're pointing in. Okay, so now let's do a similar thing in our cylindrical. Okay, and so basically what we're going to do is we're going to plug in the results from where we worked part 2, or part 1 of our problem, into the results from part 2. So let me go ahead and scroll up and we'll look where both of those things were. So here's where we solved for part 1. So here are our cylindrical coordinates. So we're going to take this 6.32 for rho, 108.43 for phi, and 3 for z, and we're going to plug that into this expression here. So we see we're going to have a rho component and a phi component. So we're just going to plug this in for rho, phi, z, phi, rho, phi, z, phi. So we're going to plug it in all of those cases. I'm not going to go through and show all of that, but it is written out explicitly in the notes on Canvas. So I will write that we're going to plug in rho is equal to 6.32, phi is equal to 108.43, and z equals 3 into equation from part 2. And so when I did this calculation, I've used stored values, so that means everything is going to come out a little bit cleaner, or not cleaner, but more exact. And so what we end up getting is that this vector A evaluated at our point P is equal to approximately -0.9487 in our rho direction minus 6.008 in our phi direction. Now, at first glance, that looks a little wrong because up here we had 2 positive numbers, here we have 2 negative numbers, but if we come back and we think about our 3D space, it makes sense. So our rho vector direction is going to be pointing away from our z-axis. So we can think of sort of drawing a cylinder that passes through that point. So our rho is pointing away, and our phi, remember, is our angle from our x-axis to this point. So our phi unit vector is going to be somewhere in this direction here. So when we have two negatives, we essentially mean we're going in more this direction. Now, because this phi was a larger number, we had -6 as opposed to -0.9. That means that one's going to dominate. We're going to end up with something maybe that looks a little bit more like that. And again, I'm kind of messing up drawing it, but you get the idea how that's pretty much it. We can visualize how that's the same. It's not similar to, it is the same as the 6 u of x plus 1 u of y. Okay, so finally, let's go through that same process with our spherical. So now we're looking at our spherical case. And again, we're just going to plug in our results from part 1 into our equation from part 2. So one more time, let's just scroll up through here, just so I don't have to copy this big mess of an equation. All right, so here was our results from part 1. So we found that our spherical representation of point P was 7 for R, 64.62 for theta, and 108.43 for phi. And we're going to plug that into our result from part 2, which was this huge mess here. And so I'm not even going to bother highlighting everywhere that we're going to substitute, but of course anywhere we have an R, a theta, or phi, that's where we're going to be substituting in. So that is not even shown in the notes because that's just a huge mess, but you can double check it. So we're plugging in R equals 7, theta is 64.62, and our phi is equal to 108.43 degrees. We're plugging that into our solution from part 2. And again, I've used stored values. So no rounding, just to get it a little more approximate. And so the end result we get is that our vector A evaluated at that point P in spherical coordinates is approximately -0.8571 in our R direction, minus 0.4066 in our theta direction, minus 6.008 in our phi direction. And again, this might seem a little odd, hard to relate to those other two directions, but if we come back up here and sort of try to visualize it, we can think about it and see if it makes sense. So of course, for our spherical, we can think of a sphere going through this point. So just kind of roughly something that looks like that. Of course, our R unit vector is going to be from the origin to the point, so that's our R direction. So our R is going to be somewhere in this direction roughly. Get rid of that circle. So our R is going to be here. Our phi, actually let me bring back that sphere for a second. So our phi, remember, is the same as we defined here. It's our angle from this. So we're going to have our phi is going to be roughly somewhere here, like with our cylindrical. And then finally, our theta is the angle coming down from this z-axis. So we're going to have our theta somewhere in this direction. So if we have negative for all of those, and again, with our phi being the one that is dominating, we're going to have sort of a negative in this direction dominating, which again is going to be the same as this 6 in our x, 1 in our y direction. So ultimately that's going to be something along this direction. Okay, so hopefully that kind of makes sense in terms of being able to visualize it. But let's say it's a little harder for you to visualize. You're not as good at visualizing in 3D space. That's perfectly fine. I have that issue a lot of the time. Another way that we can double check is that we can find the magnitude of each of these three vectors. So our magnitude of A, of course, should be the same. So it should be the same in all three of our coordinate systems. So because we're evaluating A at the same point, of course it should be the same. And sure enough, if we plug into our three magnitude equations, which is basically just taking the square root of the sum of the squares for our spherical representation, our cylindrical representation, and our Cartesian representation, we end up getting the same thing as we would expect. And so you can go through and verify this, but we get that the magnitude of A in all three cases is equal to approximately 6.083. And so that just kind of confirms that everything we did there was correct. So that concludes this example. One other thing I just want to mention to sort of keep in mind is, of course, we're not changing the point, we're not changing the vector as we go between cylindrical, spherical, and Cartesian. So we were always talking about this point P here. We were always talking about this direction A at P. We're just changing how we describe it and how we represent it. So physically, nothing is changing. We're just changing how we describe it with our numbers and letters.